Okay, I'd like to start this morning session talking to you about flood sedimentation, but I'll give the title of the lecture, Understanding the Mudrock Revolution. And the Mudrock Revolution and its relationship to the global flood is described in Scripture. And what I'm going to do is, as a symbol of a revolutionary, what I should do is wear one of those tri-pronged hats, maybe one of those wigs, maybe a little bit of machine gun ammunition over the shoulder or something like that. How should I appear as a revolutionary? Okay, but anyway, I'm leading a revolution, and that's what I tell my students. I'm leading the Mudrock Revolution. Okay, Moses lifted up the rod in the wilderness. I'm lifting up my zag tube, and I'll show you the suppressed way of thinking about mud rocks, and I'm leading you into this promised land of new ways of thinking. Is that the way to say it? Okay, mudflowman@comcast.net, that's my email, and you could also call this Mudflow Madness, okay? I'm going to look at something in a completely different way, and you might think of it as madness. Okay, my mom noticed something very early about me. I loved mud, okay, and maybe you had a kid like me, or something like that. Anyway, mud, okay, and mud is kind of interesting stuff. And when I graduated from high school, my interest in mud persisted, and I got a driver's license. And then I finished my PhD dissertation at Penn State University on what? The stinking mud of swamps and how it relates to coal in Kentucky. And so mud has been my interest and subject of study. Okay, understanding the Mudrock Revolution, I'm going to talk to you about some things that I would talk like I'm talking to my students. I'm going to talk about the planar lamination and sediment. You know, the thin, rather planar, although it's not completely planar. There's things called ripple lamination, planar lamination in mud sediments. I'm going to talk to you about my shocking statement, my revolutionary statement, and then I'm going to talk to you about critical issues that need to be addressed because I'm leading this Mudrock Revolution, and then I should talk to you about what creationists should do now to take possession of the Mudrock Revolution. Okay, I think there should be a research venue or a venture regarding mud rocks. Well, Mount St. Helens in Washington State, May 18, 1980, it erupted and created a sedimentological laboratory, essentially. And of course, these like pyroclastic flows that came off the summit of Mount St. Helens. Those pyroclastic flows left laminated sediment behind. There you see the pyroclastic flow deposit. They quickly freeze, that type of thing. And then as you look inside the pyroclastic flows, you see the fine-grained sediment and coarser-grained sand-sized particles down to clay-sized particles, even in thin lamination. Pyroclastic flow deposit with planar lamination and thin ripple lamination. And this has application, what we've seen at Mount St. Helens, I believe, to studying rocks like sandstone rocks. Obviously sandstone rocks like at the Tapete Sandstone in the bottom of Grand Canyon. So the natural laboratory of a catastrophe experience like Mount St. Helens has application to Tapete Sandstone in Grand Canyon. There are planar lamination, there's cross lamination, cross bedding in Tapete Sandstone. And laboratory models can do all kinds of things. Here's a laboratory experiment that was done to produce laminated sediment rapidly. See the laminae in that beaker or that funnel? What we do is we take a bimodal mixture of fine sand and medium sand. We stain one of the sand a different color than the other. With welder's dye, I typically do it. And what you do is you pour the sediment directly into the funnel, okay, from a beaker. And you pour it, and what happens? It naturally stratifies like this. Okay, believe it or not, it's hard not to have it unmix. So it's almost impossible to keep granular material in a mixed condition. And so I take a beaker of different kinds of sand, and I'll hand it to the students and keep them on the desk, and they're listening to my lecture, and of course they're playing with the sand, and they notice that it's hard to keep sand mixed. It unmixes in these layers rather easily. Explaining what's happening there is kind of an interesting process. But anyway, planar lamination, bimodal grain mixtures, rapid accumulation, grains flowing onto a surface, and a process called kinetic sieving. Kinetic sieving is where some particles fall faster than other particles in a granular mixture. And so anyway, these are some of the things that are noticed. I've taken this photo to people who believe that laminated sediment forms slowly, very slowly, like between summer and winter, between wet years and dry years. And I kind of put that up and say, hey, here's something you need to think about. There may be another way of thinking about laminated deposits. Yeah, and that's the kind of thing. So here's my shocking statement. There's a thing in sedimentary geology called the Bedform stability diagram. On the bottom, the mean grain size, and here is sandy mixtures right in here. Sand mixtures, okay, coarse sand right here, 2 millimeters down to fine sand, and then you have mean flow velocity up here, and you have the stable bed forms. You have the stable bed form of the condition. Of course, when the flow is moving slow, like water flow over the surface is moving slow, there's no movement. Then as water velocity picks up, you get ripples, or flatbed, lower flatbed, but that gives way almost immediately to ripples and dunes. And the ripples and dunes is the familiar thing that we see in the swash zone on beaches and on the bank of a river. Then in these experiments and in flume experiments, we discover that there's this upper stage plain bed area right here, a fast-moving water moving at about 1 meter per second right in there, and then it goes into anti-dunes. Those are upstream migrating bed forms that are dune-like features called anti-dunes. Downstream migrating dunes, the normal dunes and ripples, and then there's this upstream migrating dune form. But there's this big area in here called the upper stage plain bed stability field. And in sedimentary geology, that's what we think, well, we know about it because we can create it in flumes. But we normally think of what? The calm and placid sea and sluggard sedimentation. And so we're thinking down here, no movement or lower flatbed, that kind of thing. And so that's but the revolution I'm leading, and my shocking statement is I know the stability field for the formation of most of the laminated sediment in the geologic record, and I believe it's in that range of upper plain bed, right in there, ripples to upper plain bed. So right in here, the ripple area, and we can extend this diagram off to fine-grained sediment called silt and clay, and that upper stage plain bed becomes enormous, and that's the stability field where laminated deposits form, I believe. And so that's my shocking statement, is I know the hydrodynamic condition, or I believe I know the hydrodynamic condition for the formation of a major part of the geologic record. Take a look at the Redwall limestone. There's the Redwall limestone in Grand Canyon. You see the plain beds in the Redwall limestone. There are cross beds, there are thin lamination, there's all kinds of different bed forms. There was this geologist named Dave Sturm, a petroleum geologist, and Dave Sturm said, "Steve, you've done a wonderful job of showing that granular material can segregate quickly and form thin stratified deposits at Mount St. Helens, and your application is wonderful when you're thinking about how it might explain to peat sandstone and other things like that. But don't you ever think of explaining limestone rapidly by that type of process, because we know that limestone forms in calm and placid seas over immense periods of time from mud accumulated slowly, one grain at a time, either accumulated from breakdown of organisms on the sediment surface or moved in rather quietly by calm and placid events or process." Okay, so I got interested in studying not just the laminated sand and mud deposits, but laminated limestones as well, and massive limestone. This one limestone layer, called the Whitmore nautiloid bed, that's what I call it, in the Redwall limestone, fascinated me. I've been involved with over probably 500 nights camped out below the rim of Grand Canyon. That's right, I've lived in Grand Canyon more than a year of my life below the rim. Okay, that's amazing. But anyway, in the process of spending my time in the Grand Canyon, I focused on Redwall limestone as one of my favorite layers. And this 2 meter thick or 7 foot thick layer right here in the Grand Canyon is what interests me. And this is where we find all kinds of fossils. And so studying the fossils, how they were deposited in this layer, is of interest to me. And some things about the layer are fascinating. For example, here I am looking at a fine to coarse deposit. The top of this layer is rather fine. It's fine sand to silt size. The middle part of the layer is rather coarse. It has large objects like coral heads in it and coarse sand. And then the bottom of it is medium sand. And so I'm looking at this reverse grading and then normal grading, and the thick deposits or the coarse deposits in the middle of the bed. That's fascinating. Here's the limestones bed layer, and I'm looking down on a nautiloid fossil in the limestone. They're big. They're like the length of your arm on the average, and they have a pointy end, a tip end like that, and it's some type of marine organism. It's a squid in a shell, essentially. And that's the general anatomy of a nautiloid in cross-section. Has these curved chambers, and the body of the animal is at the wide end of the shell. And so it's a squid in a shell. You might think of it as a nautilus fossil, a coiled cephalopod, but uncoiled, straight. And some of these are over 1 foot in diameter, okay, and they taper to 1:7 ratio. So there's some in there that might be 7 feet long. Okay, so some big fossils in there. Well, anyway, fossils are interesting sedimentary objects. I know paleontologists are offended by that type of language, but they interest me as sedimentary objects. And but look at this, nautiloid fossils in the layer, and we found maybe 1 nautiloid per square meter in many places in the Redwall limestone, and they're there in large number, maybe billions of nautiloids in one layer of the Grand Canyon. The Allantitis, the North American nautiloid specialist, paleontologist, says Steve Austin has seen more nautiloids than I have. He's seen more nautiloids than anybody he knows of. And he says he may see more nautiloids than all of us together. He's seen all these nautiloids in Grand Canyon, all in one layer though. Grand Canyon strata are mostly mud rocks. This is what I want to point out. Not only limestone is sandy and muddy layers, but there's all kinds of mud rocks there. Okay, mud rocks are everywhere. Mud rocks technically are rocks which are dominated by silt and clay-sized particles. You know what silt is? Silt is down below sand in its grain size and around the diameter of a human hair. That's 70 microns, that's silt size, right? You can see silt, the coarser silt, if you lay it on a surface, you can see the dust. It looks dusty. And then, but fine clay-sized particles down there below 10 microns in diameter, those are invisible to the eye. You can't see them, but they're there, and they're a large part of the geologic deposits as well. Clay-sized particles, silt-sized particles, and sand-sized particles. They make what we call mud, okay, and that's mud rocks. And so mud rocks, most of the Grand Canyon, even the limestone layers, I look at them as mud rocks. They're just carbonate mud, calcium carbonate mud, not quartz and clay mud. Bright Angel Shale in Grand Canyon. Here we are looking for trilobites in the Bright Angel Shale. You see the shale rock. Shale rocks are kind of like the Rodney Dangerfield of geology. They don't get no respect, okay? We tend to ignore them, don't we? We look at shale rocks and say, how boring, let's go find something rather interesting, like maybe cross-bedded sandstone, or let's go find a fossil bed in a limestone layer. But, you know, the fine Bright Angel Shale is interesting. The Moenkopi Formation above the rim of the Grand Canyon is red mudstones. Mudstones are everywhere. The Manco Shale in Utah and Colorado is the dread of every road engineer, okay, because they have to build roads around Utah and Colorado, and you say the word Manco Shale, and you know what happens? They get heartburn, but just thinking about, because they got to build roads over this material, and it's mud, okay, and look what Manco Shale looks like. It's that, thousands of feet of that, okay. Manco Shale, Book Cliffs in Utah, and so that's mud rocks. Okay, look at the coal-bearing section in western Kentucky. You see the number 9 coal, 16 tons of number 9 coal. Tennessee, Ernie Ford sang that song, right? And then above it, what? Is a thick sequence of shale, a little bit of limestone here, and then there's the number 11 coal bed, and there's the limestone number 12 coal bed, and then more mud rocks above number 13 coal. And so the most of the coal-bearing layers are mud, okay, and so that's interesting. The oil-bearing strata are mostly mud. Here is, there's Royal Energy spudding in this well in Tavaputs Plateau, Utah, and they're drilling a couple miles deep, and they're putting in a gas well. And what are they in? They're in mud rocks, okay? And so what has the oil industry discovered? There's a lot of oil and gas around. It's in mud rocks, and we need a new technology. It's called fracking to get the gas and the oil out. And so mud rocks are becoming very, very important in the industry. In fact, mud rocks have made the United States of America an oil and gas exporting country. You know, we can export oil and gas, and we can, economically, we know we can find it. Take a look at dinosaur-bearing rocks. There's the visitor center at Dinosaur National Monument, built up against a slope, and there's a 50-foot thick sandstone bed right there. And it has on the face of that sand layer, sandy bed, 1,500 bones of dinosaurs. Okay, but take a look at what's around it. You have the Morrison Formation in the middle part of the Morrison Formation called the Brushy Basin member, 270 feet thick or so, and with a little bit of sand in the middle. So it's mostly mud rocks. Okay, dinosaur-bearing strata are mostly mud rocks. And then southern Alaska, mud rocks are abundant in southern Alaska. There's a Nicolay greenstone, that's ocean floor rock that's been pushed onto and docked against southern Alaska. You have the Moonshine Creek Formation, that's a mudstone formation, and Frederica Formation, volcanic mudstones in there. So there's a huge thickness of mud rocks there. And so mud rocks are everywhere. And so if you ask geologists how abundant are mud rocks, they'll usually say something like maybe half of the stratigraphic record is mud rocks, with silt and clay being the dominant size rocks. Mud rock is any fine-grained sedimentary rock dominated by clay size or silt size particles. It includes rocks like shale, mudstone, siltstone, fine-grained limestones, and many volcanic ash deposits. Okay, what the oil industry calls shale, oil shale, and gas shale, they're typically siltstones. Okay, that's a trade secret of the oil industry. Most of the oil shale production of natural gas is out of siltstone. They're actually getting production out of that. Okay, what can you say? Like the Manco Shale, dominated by planar lamination and cross lamination. Okay, planar lamination is perfectly parallel, but sometimes you're following those very thin parallel laminations along, they'll turn and truncate the layer below. That's called cross lamination. So cross lamination and planar lamination are the dominant sedimentary characteristics of mud rocks, and especially these fine shales and siltstones. And then they're very abundant, composing about 3/4 of the stratigraphic record. If you think about the extent of these mud rock and that type of thing, something like certainly over about half of the geologic record would be called shale. If you add the siltstone that's on it, you'd be certainly about 3/4. So how do mud rocks form? Okay, here is the old way of thinking. How do mud rocks form? Planar lamination forms how? By particles raining down vertically onto the bed. Okay, you imagine this. Mud particles, silt-sized and clay-sized particles, falling vertically in dispersed condition directly on the surface of sedimentation. That's this idea of planar lamination. That's the old way of thinking about planar lamination. The revolutionary way of thinking, the revolution I'm leading, is no, the particles don't fall generally vertically. They fall onto the surface inclined at 15 degrees to horizontal, like you see here in this diagram. And that's the way I think the typical mud bed forms. Okay, planar lamination and cross lamination are primary structures in mud rocks. How does the lamination form? And here, giving you two options. Cross lamination, this is a feature of mud rocks, and you see the general appearance of it. When mud rocks become compressed and compacted, what happens? They lose their they lose some thickness, and so the planar, it appears to be very planar, but if you look at it in detail. Here's the typical way of thinking. Here's the MIT short course by John Sutherland. Here's his course notes, taught in 2006, planar stratification. Planar lamination can develop whenever there is fallout of suspended sediment onto the planar sediment surface in the presence of currents that are too weak to transport the newly arriving sediment over the bed. Planar lamination of that kind is at once the easiest to understand and philosophically the most natural. Whenever there is a planar bed surface with particles raining down from above from a fluid, that is not moving fast enough to move the particles once they form. Planar lamination is formed, provided only that the nature of the sediment that is raining out fluctuates in one or more ways with time. Do you understand the conventional thinking about mud rocks? They rain down slowly. There's an oscillation in the character of the sediment in some way, back and forth, and so that leaves the lamination. Take a look at some of the, how do you like that language? Okay, too weak, easiest to understand, most natural, not moving. You see the way of thinking? I'm leading a revolution against that, okay, that way of thinking. I'm thinking completely outside the box there, okay? That, it may be very natural, okay, and the currents are weak and not moving. It's easiest to understand. Does it sound like an agenda-driven thought pattern there? It does to me, and so that's what I'm rebelling against. Planar lamination of mud rocks, a 20th century misunderstanding. Calm and placid seas transgress the continent during millions of years. The still water far offshore allowed the finest particles to rain continuously by extremely slow sedimentation. A particle, a mud-sized particle down about 4 microns, a clay-sized particle, takes about 3 days to settle 1 foot through calm water by Stokes' law. So dispersed clay particles, by their hydrodynamic condition, settle very slowly, extremely slowly in calm water. And then mudstones are the direct result of the enduring cratonic seas during the passage of millions of years. Can you imagine the way they're thinking about mud rocks? You know, the ocean slowly transgressed the continent, and we had the ocean over the continent, and we had this shallow epicontinental sea, and then, of course, mud particles are being brought in from rivers and in the coastal environment. These particles rain down very slowly. Therefore, a uniformitarian view explains most of the strata record. Okay, if mud rocks, the siltstones and sandstones, or siltstones and mudstones are three-quarters of the rock record, then yeah, a uniformitarian or somebody of this mindset would say, yes, the geologic record requires millions of years. Steve Austin's shocking statement after 36 years of employment as a professional creationist geologist: I believe I understand the hydrodynamics and the fluid mechanics of the flood process, deposit planar lamination and cross lamination, and approximately 70% of the stratigraphic record. Is that a shocking statement? Okay, I think I understand the hydrodynamics of that, and the short answer is upper stage plain bed in that type of stability field. And the upper ripple in this range of 0.5 meter per second up to about 1 meter per second, that's not a calm and placid sea. Okay, that's something quite different. So that's my shocking statement. The Bedform stability diagram has been worked out with quartz sand and flumes. Unidirectional water current does not include silt-sized particles, which are over on the other side, and so it's not worked out for sand-sized mud floccules. Okay, and I'll talk more about that here in just a minute. The critical issues of mud rock revolution and the formation of planar lamination: particle character, dispersed particles or floccules. Now, the uniformitarian, the tired and outdated theory uniformitarian mindset says that all particles are dispersed. Mud particles, what happens is they're dispersed and they fall slowly, okay? But mud can clump together and form floccules. Are you familiar with floccules? I'll talk about flocks here in a minute. But mud has a tendency to form in turbid conditions, especially when concentrated. It clumps together and forms these little flocks, which are sand-sized clumps of silt and clay-sized particles. The particle trajectory, is it vertical from just hindered settling of individual dispersed grains falling, or is it inclined with gravity, current kind of settling? The velocity gradient above the bed, is it lower plane bed and slow movement or no movement, or is it upper stage plane bed? That's the velocity gradient above the deposit. And then the boundary layer dynamics, at the boundary between the sediment and the water, there are some very interesting features formed there, continuous or discontinuous. And then we have the rate of laminae deposition. The issue is slow or fast. And is that an option? Is there an or? The evolutionists say no, slow. All mud rocks form slowly. There is no fast way to form mud. Okay, well, I would differ. How am I doing time-wise? Okay, doing okay? All right, how much time do I have?
You have more than a half hour.
Cool, okay, good. So I can spend some time talking about this. The particle character, dispersed particles or floccules, right? Okay, that's an important issue. Mud particles almost universally clump together to form floccules. There are, and I'll talk about how you can defeat the floccule formation process in a sedimentology lab at a major university when we're trying to encounter dispersed mud. Okay, I'll talk more about that. But aggregation makes floccules because sticky organic molecules adhere to muds. Now mud, clay-sized particles especially, have this ability to be sticky. And organic compounds especially stick to those small particles. And mud is dirty, you know what I mean? It has organic on it. And the molecular or the mineral structure of clay is like a peanut butter sandwich. Bread on top and bottom and sticky peanut butter in the middle. And the peanut butter sandwich kind of model of clay formation means it is electrically and organically able to clump together very easily. And that's called flocculation. The aggregation makes floccules because of sticky organic molecules, also because of electrostatic phenomena. And anyway, the floccules can agglomerate within less than 2 grams of mud per liter of water. So take a liter of water and put 2 grams of mud-sized particles, of silt and clay-sized particles in a liter of water. That would seem like a rather dilute solution, you would think. But it can happen that low amount of mud can clump together to form this, these floccules. Flocculation, even from dispersed conditions of mud, is hard to defeat. Floccules can survive moderate turbulence. And what defeats flocculation is turbulence. If you can get turbulence there, especially at the sediment-water boundary, that turbulence can break apart floccules. And flocks have the settling properties of sand. Flocculated mud falls like sand particles. Okay, how fast does it take sand to fall through a foot? Just a matter. Well, we got a tube. We can understand that and look at that. It falls fast. The details of mud floccules, here you see it under the microscope, and with scanning electron microscopy, we study mud floccules. Anyway, you can see the clumpiness. These are particles that are agglomerated into fine sand-sized particles, and then they make this, and here we're looking at a flock right here with a whole bunch of clay-sized particles that are clumped together. It's very easy to find these in the mud rocks. And again, polished surfaces and scanning electron microscopy is the way I like to look at mud flocks. Mud floccules in the graduate sedimentology class at a major university in 1970. Okay, here's what happened. In 1970, at the graduate level sedimentology class at San Jose State University, mud was washed in distilled water with some type of detergent. Now what you do is you wash your mud. We were given the assignment by the professor, measure the fall velocity of those clay-sized particles. And can you confirm Stokes' law, the settling velocity of particles? And so here's what we were told to do. Take your mud sample and bring it in, and you're going to do sedimentology of mud. But when you bring it in, be careful to wash your mud sample in distilled water with some type of detergent. Why? Because you want to get rid of all the organic goo that's hanging on the outside of your mud particles, right? And then, okay, soak it in bleach. Okay, sodium hypochlorite is especially useful, and you soak it in bleach, which what? That further oxidizes any organics that are sitting on the exterior of those silt and mud-sized particles. And then there was this amazing thing. We were told about it. Underneath the counter in the sedimentology lab, under the sink in the sedimentology lab, is a box. Okay, and the box is a box of Calgon. Okay, wonderful compound, Calgon. Sodium hexametaphosphate. And you put a little of this in your solution, and that also, we weren't told about doing it, but the word got around that there's some Calgon in the cabinet, and boy, did it work wonders. Okay, so all those students who weren't washing their sediment and causing it to fall through the graduated cylinders, they were watching it, they were distressed because you could see all the clumping going on, the flocculation, and everything fell out very rapidly. But we had to defeat that, and so that was the way we did it. After treatment, Stokes' law worked. Okay, we got slow settling of particles. Okay, there it is. Reasons for treatment. Everyone knows how mud particles must have settled to make shale deposits. How did they settle? Okay, in 1970, all mud settles vertically through the sediment column rather slowly. Okay, and we have to simulate that, and so we have we're aided by detergents, by bleach, and by Calgon. The mud was washed in distilled water, sometimes detergent soaked in bleach. Boy, that worked good. And then we did, we're told about Calgon. And what Calgon does is sodium hexametaphosphate. What it does is it grabs on to cations. And the cations in water, because water's not distilled water in the environment, cations cause clay particles to become electrically attractive to each other in the presence of especially like sodium and potassium and calcium and magnesium. That's what hard water is, okay? And so sodium hexametaphosphate is a water softening compound that causes Stokes' law to work. Okay, that's just the thing about it. Okay. San Jose State University. That's when I took sedimentology, okay? And they all, yeah, that's a standard thing you do. You observe sedimentation of fine particles, and obviously you want to know whether Stokes' law works, and they settle slowly. But we taught that they settled slowly, so we had to simulate that, and that's how we did it. Particle trajectory, vertical or hindered settling, or inclined and gravity current settling. Okay, there's two options here. Vertical settling of dispersed particles causes hindered settling and slow process. Inclined settling of floccules can occur on slopes, within layers, and within pipes. Okay, and this inclined process is very interesting. I'll get more onto it. And then upon slopes or within inclined layers, floccules concentrate in a dense layer and a clear layer. And that's called the Boycott effect. Okay, and I'll tell you the Boycott experiment. Dr. Boycott, during World War I, was a medical doctor, and he would separate out blood cells from the liquid plasma of blood in his laboratory in Europe during World War I. And he would collect the blood sample and then allow it to settle slowly, right? And you collect the blood cells at the bottom. But one day, he took a lunch break, and his test tube rack was sitting there with blood samples in it, vials of blood samples, and something kicked the blood samples off of vertical. And what happened is the test tube rack got tipped off at a 6-degree angle, and he came back after lunch and he found something very interesting. All the blood cells had fallen to the bottom of the mixture very rapidly at the end of his lunch break, and he came back and he said, wow. And so I have a new way of separating out blood cells from the liquid serum of blood, and so he was known for that. And so inclined settling and the Boycott effect. And the dense layer can become a gravity current. Once you get particles separated out in a dense slurry, or they can become a gravity current, quickly moving particles and fluid. Okay, types of particle settling. Vertical settling with dispersed particles, that's usually called hindered settling. Do you see the idea there? The individual particles are dispersed through the mixture and they fall vertically. They can fall fast and they make turbulent wakes as they fall, that type of thing. Okay, or inclined settling. As in inclined settling, particles come together and they settle as a current, and that's the Boycott settling. Okay, I've got this thing called a zag tube. Okay, zag tube. Illustrated by the zag tube. Okay, does everybody have one of these handy? Okay, let's make sure all your particles are at one end or the other. Okay, and you can look at this. Okay, and then here's what I do. I'm going to have vertical settling, because I watch my particles settle, and they come down in a dispersed condition, each of the particles falling individually, separately, and they fall rather slowly through the mixture, through the fluid, and they make a turbulent wake, and that's called hindered settling. Now you can simulate this process of inclined settling by flipping it over and turning it at 60-degree angle. Okay, 60-degree angle. Now watch what happens. The particles quickly form a clump, and the clump falls through the fluid. Inclined settling versus vertical settling or hindered settling. Okay, okay. Take a look at that a little more closely. What happens? The particles clump together, form a sediment water mixture, and the sediment moves the fluid. Okay, or with the fluid. Okay, so it's an interesting phenomenon, at least for me as a sedimentologist. Boycott settling, current settling. You create a counter current, and so what do you have? You're having a slurry flow down the inclined tube. You see that? And it's the water and the sediment move together as a mass, and then there's a recoil current, that counter current that moves. That's the other way that happens. Okay, you can create this type of settling, inclined settling, in a device called a Racetrack flume, and here it is. You have this long flume, typically a meter deep, several tens of centimeters wide, and you have this observation window over here. You have the turning upstream and downstream turning sections, and then you have the drive system for the flume over here. And it's Barney Rubble technology. You have this paddle that drives the flume, and we'll talk about why you have a paddle-driven situation. This simulates long distance of flow of a slurry. But anyway, the particles and the fluid are propelled through the flume from above by scooping action of paddles. Okay, and the paddles get the mixture going in the flume, and then you can put your mud samples in there. Remember, mud as little as 2 grams per liter. That can induce flocculation. So just about every situation you put your mud in the flume, it creates layers. The observation window, you can see some of the lamination that was formed by the mud moving through the flume. And it's illustrating, here you see the process. Okay, what they did was, in the middle of the experiment, we dropped magnetite particles, a magnetite fine sand, onto the sedimentation surface, and then we allowed the flume to continue to operate. And so putting magnetite in there, a sand layer, makes a stable flat bed and allows the particles to segregate easily and makes a marker. And so you can see a time sequence here. So these little laminations often terminate, and so what you're illustrating here is ripple lamination. Ripple lamination, or fine, a very gentle kind of non-flatbed feature formed. We can actually do the hydrodynamic conditions, but at about 25 centimeters per second in a Racetrack flume, this type of sedimentary structure forms, planar lamination and cross lamination. So certainly the velocity of 25 centimeters per second right in there, all the way up 40 centimeters per second. So you get floccule streams and migrating flock ripples in the flume. So the flume makes mud rocks rapidly, okay? And it makes it in this region right in here. So this upper ripple phase, and then as this extends off into the mud particles, it obviously a plain bed and ripple lamination is the way that things form. There are not dunes in that, big dunes. They're ripples and flatbed. The Mudrock Revolution. Now here's what's interesting about the Mudrock Revolution. The planar lamination in the New Albany Shale, Devonian, Indiana. The Chattanooga Shale is the equivalent down here in Tennessee. But when you make a polished surface, what you can see is ripple lamination. You can see these beds terminate. And what does that mean? That means the particles are not falling vertically onto the sedimentation surface. They're falling at 15-degree angle to vertical. In other words, this is current that's bringing in the mud, and it's separating out rapidly. I That's the revolution I'm leading. I'm thinking all about mudrocks from that different perspective. Okay, and the last thing is the sediment-water interface, and there's this boundary zone. There's a discontinuous mixing above a planar bed at Froude numbers greater than 1. Okay, and at Froude greater number 1 are fast-moving currents. The upper and near bed layers separate into what's called a bursting or unstable boundary. And that boundary effect, within just a few millimeters, maybe even a centimeter or so, that's the action area where all of the particle segregation occurs that makes plain beds. And here in the flatbed field of sediment, in that boundary, the oscillation of that boundary creates, I believe, mud layers. And the technical name for this phenomenon is called Kelvin-Helmholtz instability. Okay, Kelvin-Helmholtz instability. It's worth Googling that and seeing some of the videos. People create flow boundaries with this type of phenomena. It's a bursting phenomena, laminar to turbulent. And okay, everybody's seeing clouds. And there's 2 layers of the atmosphere that are shearing, and the shear at that boundary creates a waviness, and that waviness creates an oscillation, and that oscillation from laminar to turbulent, whatever that's going on there, creates the mixing at that boundary. And that's a Kelvin-Helmholtz instability. Discontinuous mixing above a plain bed at the boundary within high velocity fluid flow, a Kelvin-Helmholtz instability develops. Laminar flow boundary through a period of several seconds becomes turbulent, then becomes laminar again, it relaminarizes, and then the alternation of the laminar flow followed by turbulent flow process, a plane parallel layer of coarse and fine sediment, about 2 millimeters thick, is formed. Okay, it's a no-brainer. That type of thing, I believe, is the way mud particles separate out rapidly. When you're driving and you open the back windows of your vehicle and you hear that pup 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 pup, remember hearing that sound? That is a Kelvin-Helmholtz instability. As you look around in clouds, you can see it, that type of thing. But there's an alternation between turbulent and laminar flow. That is extremely important in the boundary layer for forming these things. And so here's a flume experiment with fast flow where we, unidirectional flow, we have a concentrated slurry of particles. We have this, the concentration becoming laminar in this flow boundary, and it creates this, the bedding. And then here you see the bedding is produced. You can see the lamination generally running along the window, and so that's the type of thing in the flume that is very interesting. So I think I know the hydrodynamic conditions for the formation of 75% of the geologic record, and I'm leading this revolution. Rate of laminae deposition, slow or fast? Modern examples of slow laminae deposition have doubtful application to mud rocks. Flume experiments make laminated muds in the transition zone from ripples to upper plain bed with a Froude number a little bit less than 1 by low amplitude ripple migration. And this ripple migration creates the ripple lamination, or in faster moving flow, even plain beds, flat layers. And then flume experiments make laminated fine sandy mud in upper plain bed on a flat bed, probably by a bursting process at a flow boundary, an alternation between laminar and turbulent flow. So here's the mud rock revolution. silt varves in Lake Walensee in Switzerland are definitely non-annual, formed by episodic river floods. People have been telling us that thinly laminated deposits represent years, many years, and that whole idea of laminations or varves forming slowly is out there. But there's examples. Dated foundations in Lake Walensee in Switzerland have non-annual varves over the top of the dated foundations. They form rapidly, probably episodic river floods. Whoops, sorry. Okay, episodic floods in the Eel River in California make planar lamination on northern California continental shelf from density flows of sediment. And during the floods and the storms, the rivers come in with mud, and the mud is high concentration, so it settles out in the water column. As it enters the ocean, forms these underwater slurry flows, and that's a density flow, and it makes particles deposits particles on the California continental shelf during those events, and they fall out not vertically, but a 15-degree angle from vertical. And the so-called varves in the Green River Formation are non-annual cross-laminae, probably deposit from episodic sediment flows, not from slow and gradual process. Somebody said 11 million varves in the Green River Formation must require 11 million years for the Green River to form. There's no flood there. And then I can tell you stories about sedimentologists and people who have been in this field that need to think. Well, for example, Glenn Morton, he didn't think critically about laminae formation, and he left the fold of creationists and now became a critic of flood sedimentation. Mudrock revolution, fine-grained sediment. The quote here is from Bohack and McQuacker. McQuacker and Bohack, Science Magazine, December 2007. Fine-grained sediment is seldom deposited as individual grains, but commonly organized into grain aggregates. Flocculation is everywhere. That's what they're saying. These studies indicate that many of our preconceptions about fine-grained sediment are naive. What is that saying? That we've deceived ourselves, or we're not using our logic process correctly. And then here's what Bohack and McQuacker say: mudstone science is poised for a paradigm shift. Okay, what does that mean? What do you think is going on there? They're thinking that we need to completely ditch this, the slow and gradual way of thinking, and let's get on with studying mud rocks the way they should be studied, with a paradigm shift. In other words, you need a revolutionary like me to lead your thinking process. Okay, the mud rock revolution. Okay, stratification next to volcanoes in modern lakes and on continental shelves today forms today very rapidly. Stratification in flume experiments forms very rapidly. Racetrack flumes are a special way to do this. Mud rocks are dominated by the structure of rapidly deposited sediment. Exclamation point. See the exclamation point there? Mud rocks are dominated by the structure of rapidly deposited sediment. We can make a machine that can make that type of structure. Steve Austin's shocking statement after 36 years of employment as a professional creationist geologist: I believe I understand the hydrodynamics and fluid mechanics of the flood process that deposited planar lamination approximately 70% of the stratigraphic record. Is that a shocking statement? It's audacious or revolutionary. What do you want to say? Okay. Anyway, I understand something about that. Okay. Steve Austin's shocking conclusions on mudrocks: planar lamination in mudrocks, upper stage plain beds. The technical term is Froude number greater than 1. A bursting flow boundary process occurs that causes at a velocity of about half a meter per second, and aggregation of of beds that form about a millimeter per second. So I can deposit mud at a millimeter per second in these flume experiments and make laminae rapidly, very rapidly, and there shouldn't be any doubt about that. If you want to build the machine, let's do it. Okay, cross lamination, ripple to upper stage plain bed with a Froude number less than 1. That means that's a less severe hydrodynamic condition. Variable boundary flow velocity about 20 centimeters per second. Aggregation rates of approximately a millimeter per second. So at an aggregation rate of a millimeter per second, how long would it take to deposit the Hermit Formation in Grand Canyon? Hours? A week? Something like that? Okay. Mud rocks are deposited very rapidly under flood conditions. That's what I call mud flow madness. Okay, and I'm leading this trek into the journey into the promised land of interpreting mud rocks with currents. What creationists should do now to take possession of the mud rock revolution? Hey, we could actually do this, build the machinery to make it happen. Like build racetrack, large-scale racetrack flume. Restate the critical mud rock issues as easy to understand talking points. I think we need to say that. There's that old, tired way of thinking, and there's this new way of thinking. We need to carefully illustrate that. We need to build a racetrack flume and make planar lamination of muds, do it, and make our experimental conditions real. Take possession of the scientific discussion by being in the forefront of discussions and research. Be the world's experts. That's what we need to do. We need to do this. And why should creation build and operate a racetrack flume? The short answer in the flume is you need to control turbulence. Turbulence. And see the paddle-driven flume? That's what it does. It controls turbulence. If you put a vane rotor pump in this machine, it will introduce turbulence into the machine, and what does that do? That breaks the floccules apart and defeats the flocculation process. We want to take control of turbulence, controlled turbulence. Artificial turbulence in straight flumes breaks up floccules. That's what happened in the history of simulations, as people use straight flumes, and they ran pumps, and they put it through pumps and allowed it to happen. So how about a racetrack flume? We need to build it. Wouldn't it be great? Needs collaboration of sedimentologists and engineer to build it. We need to relate laminae formation to field outcrops of mud rocks, so you need a geologist and an engineer working together. You need about 2 years to perform the experiments, okay, and you need to publish results. It's a no-brainer, right? That's the kind of thing we need to do. And let's make fine laminated sediment in the upper flatbed, plain bed stability field, and let's start doing it. In other words, we should be leaders. Modern observations and flume experiments have revolutionized sedimentation thinking with the understanding that strata deposition was a very catastrophic process. And understanding the mud rock revolution, we've talked about planar lamination and sediment. You've heard my shocking statement. I know the hydrodynamic conditions. that deposited 70% of the geologic record. The 5 critical issues that are leading the Mudrock revolution, I've talked about those 5 issues, and then what creationists need to be doing now. Okay, understanding Mudrock revolution as a global flood, and the global flood is described in Scripture. Is it mud flow madness, or is this real? Okay, we could make it real, okay? And theory and practice need to come together. And so that's my lecture today. Thank you.